Hey everybody, as you can see from the topic, notes, video C, what we're going to be doing is sketching f prime from f. We're going to be sketching the derivative graph from the given graph. Sometimes we're going to be given an equation for the function, and you might be thinking, okay, well, graph the function and then find the derivative using the differentiation rules we've learned. Find f prime, type it in the calculator, graph that. That's fine too. That's an easy way to sketch f prime from f if you know the equation of f and can find the equation of f prime. And that kind of gives you something to work with. But we're going to try and build to the point where what happens when we're not given the equation for the function, but we're given a graph instead, just a graph, and we're supposed to produce the graph of the derivative from that. So that's what this video is about, trying to put our minds around how to sketch a slope graph given the graph of a function. All right, let's start with a well-known function, the square root graph. So what I'm going to do here is I'm just going to draw a quick sketch of what that looks like to us. Okay, so we can examine this graph and we can see that it's increasing slowly, but it is increasing off to infinity. So some of the things you want to think about when you're going to come down here and produce a slope graph, a derivative graph. Okay, and I'm just going to leave this blank here. I know I can find the derivative equation because I can use the basic power rule after a rewrite here. But we're going to try and avoid doing that. We're going to use that to help us check our derivative after we sketch it. So we know that what belongs here is a certain equation that we can find. All right, so studying this graph right here, just some things you want to notice would be, hey, this graph is increasing, rising slowly, the further out you go, across its whole domain. So if you wanted to kind of put numbers to different locations on this graph as far as slope values are concerned, let's just kind of study maybe this point right here. Okay, we know that if we drew in the tangent line to the graph right there, that the slope of that tangent line would be positive. So what we do is, to create the slope graph, is we look at the corresponding x value, okay, right here, whatever we call that, okay, and we come down here. I'm just going to kind of draw this dashed line right here. Okay, and I'm coming down to the same x value on my f prime graph. Well, what I'm going to do is I'm going to use this slope value as a y-coordinate to plot a point down here. Again, I'm going to use the slope value, whatever it is, and plot it as a y value at the corresponding x down here. Well, come back up here. You know the rate of change here at this x value is positive. Do I know what the number is? No. I can make a number up. I'm just going to say maybe it's positive 1. I'm just guessing. I'm just going to say that the slope of this tangent line is positive 1. I know it's positive, a positive number, because the graph is rising. I don't know exactly what it is, but I'm thinking, I'll call it 1. So that gives me something to work with down here. Okay, when I look down here, well, if I'm going to plot that slope value of 1 as a y value on my f prime graph, I'm just going to make up another y value and say, you know what? Maybe that y value is 1 right here. So I'm at the same x, okay, as I am on my regular graph, but this time I'm not graphing the y-coordinate on my slope graph. I'm graphing the value of the slope down here. So that's the point I'm going to plot there for that corresponding slope value. Okay, now from this point right here, I'm just going to move to the right, and I'm just going to kind of notice that the rate of change is still going to be positive, but less. The tangent lines are less steep, if you will. They're kind of falling, getting closer to 0. And I know you can see that. So at the corresponding x value, so maybe let's just pick on this point right here. Well, that slope value is going to be smaller than the previous slope value. So if I plot that value, okay, it's going to have to be along the corresponding x down here. Okay, it's going to have to be a y value that's smaller than the previous slope value. So maybe something like that. As you come back up to the regular graph and you work your way across the graph, you can see that the tangent lines are getting less steep. So their values, their slope values, are approaching 0. So if I move across this graph down here, the slope graph, f prime graph, I know that these y values have got to be getting closer and closer to 0 because the graph is getting flatter and flatter here. So I guess the next question is, will I ever intersect the x-axis down here? That is, will this graph ever be 0? No, It's increasing across its whole domain slowly the further out you go, but I'm never going to reach zero. So that tells us some information down here about this graph. That tells us that this graph right here is going to be approaching, the f prime graph is going to be approaching zero the further out you go. So think of the x-axis as an asymptote, or horizontal asymptote, for the slope values. Okay. Well, this is good. This is fine. This is part of the graph. So, sometimes it's just best to take a graph by section and kind of work with it. So I think from this x coordinate to the right, values greater than this x value, I think we've kind of got a good idea of what these y values are corresponding to up here. Now it's time to start working our way back, say, to x equals 0. Well, let's kind of focus our attention right here in this region, which is this region we need to produce a graph. All right, well, the further I go back to the left from this x value right here, we can see that our tangent lines are becoming more steep. So as I kind of walk my way down here, I know that as I work my way back to the left towards 0, the tangent lines becoming more and more steep have greater slope values. So those plot as y coordinates down here. So these y values that I'm plotting are the slope values of the corresponding tangent lines. Okay, well, we've studied this graph before, and we know that this graph, y equals square root of x, is not differentiable at x equals 0 because it has a vertical tangent line. So at x equals 0, how do I plot the value of the slope, when the slope is undefined? Well, I don't. So I guess we can kind of think of the y-axis, the positive y-axis, as a vertical asymptote for us. So this graph will just become steeper and steeper right here. So this is actually the derivative graph for the square root of x. And we just did it by sketching and thinking about the slope values and how they correspond as y values when plotted down here. So just a general overview. Look at the given graph. It's increasing everywhere, which means that if it's increasing, all the slopes are positive. If all the slopes are positive, then these y values must be in quadrant 1, where my y values are positive. Again, the trouble spot right here is that we have a vertical tangent. This graph is not differentiable at x equals 0. How do we plot that y value? Well, we don't. We just assume that the positive y-axis then, or not assume, but we know that the positive y-axis becomes a vertical asymptote. All right, notice that the square root of x doesn't have any part of the graph over here, so I should have no part of a derivative graph over here. It just takes practice. Okay, that's curve sketching, sketching f prime from f. If you wanted to confirm this graph, and I encourage you to do so, okay, I would suggest to you to rewrite this, find the derivative using the power rule, 1/2 x to the negative 1/2, typing that into your calculator, and seeing that when you graph it, that you do in fact get this graph. Right? But the skill of producing a slope graph and f prime graph from f without having to find the derivative is a good one. All right, let's practice another one. All right, this is an easy enough function. Downward opening parabola with the vertex at 1. Looks something like this. Okay. If I wanted to graph the derivative, because it's an easy enough equation to differentiate, okay, I know I can find the derivative using the power rule. And then I would know, I'd be familiar with that function too, and I could graph it pretty quickly and I'd be done. Okay, but let's take our new skill here and produce a slope graph and then confirm it by doing what I just mentioned. All right, so I'm going to line up vertically. Look what I'm doing. I'm lining up vertically underneath this axis, an axis for the f prime graph. Okay, well, what's different about this graph than the previous graph? On this graph, I have a maximum. We've been talking a little bit about a maximum and a minimum vertex, the vertices where the rate of change is 0. The graph is pausing. It's thinking, do I continue up or do I continue down or return to down? And at that point right there, we say the rate of change is 0. So if I'm trying to produce a slope graph, I'm looking for kind of interesting places. This graph really didn't have an interesting place other than maybe x equals 0, where the graph is not differentiable. I'm going to look for maxes and mins because they tell me, if I look at this graph right here, that the rate of change is 0. Well, that's a slope value. So at the corresponding x, which happens to be x equals 0, I'm going to come down here and I'm going to plot the value of the slope, which is 0, okay, right here. So at x equals 0, I'm plotting y equals 0. So my f prime graph is going to cut through the x-axis right here at the origin. Okay, once you've established maybe your zeros, that's kind of where I would start. I'd look for mins and maxes, flat spots, more about flat spots in a minute, also known as saddle points. I'm going to look for my zeros, my zero slopes to plot as x-intercepts down here in my f prime graph. Then I'm just going to start working my way through the graph. So working left to right, I'm going to kind of notice what's happening. On my way up to the maximum, my graph is increasing. Well, the rate of change at any x value when the graph is increasing is going to be positive. Just kind of study the slopes of the tangent lines. Right here, the slope is pretty great. I mean, it's pretty large. Okay, the tangent line is pretty steep. But when you move to an x coordinate that's closer to 0, here, well, the slope of that tangent line is not going to be as great as, say, the slope of the previous x. That is, the tangent line is less steep. And certainly as you get closer to this 0 slope, right here, this tangent line, you know, the slope is still positive, but it's not going to be as great as the previous slope values. So sequentially, I'm trying to look from left to right, studying the values of these slopes and getting an idea of where they plot down here. All these slope values are going to be positive, so the whole graph of f prime is going to be in quadrant 2. So I kind of looked at this x value right here. I'm going to say that slope value is 10. So if the slope value is 10, I'm plotting 10 as a y coordinate. I'm just going to say that's 10. Okay, working my way up through the graph, which means I'm traveling to the right. Okay, if I look at this x value, well, that graph's not as steep there. It's not rising as quickly. So I'm going to just say maybe that slope is 8. As I move across the graph, the slope of this tangent line is smaller than 8. Maybe it's 4. So I'm going to look at that corresponding x down here and plot it as 4. Okay, eventually I'm going to get into a 0 slope. And as you guys can see, these points that are lining up this way suggest that the derivative graph is coming in to the origin like this. And certainly the further down you go on the regular graph, the more steep the graph's going to be, which means the slope's greater, so the y values will get higher. So I guess, again, start with the mins and maxes. Those 0 slopes are x-intercepts down here, and then just work your way through the graph. Okay, now we need to produce the slope graph over here, either in quadrant 1 or 4. So we notice the graph is decreasing. Well, the graph is decreasing, all the rates of change are negative. So those slope values will plot as negative y values down here, so my graph should be continuing into the 4th quadrant. Okay, let's kind of get a general look at it. The slope of the graph right here next to the vertex is going to be negative, okay, but at kind of a small negative number. So it's underneath the x-axis as a y value, maybe about right here. Okay, work your way down the graph. The graph starts to fall more rapidly, so the slope of that tangent line is going to be smaller than, or in steepness, I guess you could say it's greater than, the previous slope. So that plots as even I guess you could say a more negative y value, if that makes sense. Okay, and the further down you go on the graph becomes more steep in a negative way, corresponding to even a smaller y value. So what we end up having is a quadratic equation's derivative is a linear function. Okay, so, and if you come back to the equation, it kind of makes sense because when you find the derivative of 1 minus x squared, you're going to get a linear equation. It's 1 degree less than quadratic, its derivative is linear, and that certainly looks like the graph of negative 2x. Okay. All this to build towards producing a graph of a derivative without giving an equation. Okay, so just practicing some more. Okay, if the regular graph is 3x plus 2, we certainly know the y-intercept is 2, a slope of 3. The regular graph is going to look something like this. We all can easily find the derivative, and that's going to be 3 by using the power rule, or just knowing that the slope of a linear function is constant rate of change, so the slope is going to be 3. So no matter where you stand on this graph, the slope of the tangent line is always going to be positive 3. So at every x value down here, I'm going to be plotting a y value of 3, because the slope here at this x is 3, okay, at all x's would be 3. So at least kind of show some tick marks that indicates what your slope is, okay, if you have an equation that you know what the slope is here. Okay, so, and then using the power rule, that's 3. Okay, we'll continue in the next video.